New topic today, chapter 5, exponentials and logs. Okay, so we are going to sketch exponential functions. We're going to differentiate e to the x, which is really easy. We're going to introduce you to Ln, which is the natural logarithm, and we're going to use logarithms to estimate the values of constants in non-linear models. So we're going to it's going to be a non-linear model, but we're going to rewrite it in the form which is going to be able to compare it to y equals mx plus c, which is quite nice, so we can put that onto a linear model. And then we're going to have a look at modelling with exponential functions, which is real life applications. It's really good to see how we use this in the real world. So we're going to look at graph transformations. Okay, when we think about graphs, let's go back to basics. Okay, let's really think about this. And if we have to spend a little bit longer on it, it doesn't matter, because graphs, we have to do a lot of graphs. Let's really break it down. Okay, so when we think about functions, do you remember in GCSEs we had f of x? Okay, and if I taught you, it would always be, if we had f of x plus a, I would always say, is it inside or outside the bracket? Is it? What is it? Inside. Who does it affect? X. What do we do to all the x coordinates? We minus a. We do the opposite, okay? Because it's trying to trick us, isn't it? Okay. And then if we have this, f of x plus a, inside or outside the brackets? Outside. Who does it affect? Y. What do we do? What it says. Okay? So in this case, let's say our coordinates were 0, 4. Okay? If it's inside the bracket, we do the opposite. It says add a. We're going to take away a from all the x coordinates. So instead of 0, 0 minus a is just minus a. And then 4. But then for the second one, if we had 0, 4, okay, inside or outside the bracket? Outside. Who does it affect? The y coordinate. What do we do? Exactly what it says. Add a to all the y coordinates. It's going to have 0, 4 plus a. Okay? We should be fairly comfortable with this. If not, we do need to go back and get comfortable with this. Okay? I'll put some links for extra videos. So, if we think about y equals 2 to the power of x plus 3, in terms of is it inside or outside the bracket, okay, what is our function here? What do you think our function is? So, our original function here is y equals 2 to the power of x. This is our original function, okay? And now we have y equals 2 to the power of x plus 3. So applying a similar understanding of this. Is it inside or outside the bracket? It is inside the bracket, yes, because our function is to the power of x. And because we're doing x plus 3, if it was outside, okay, we'd have y equals 2 to the power of x plus 3. So, is it inside or outside the bracket? Inside. Who does it affect? It affects x. And what are we going to do? We're going to minus 3 from all the x values, which means we're actually translating it to the left, aren't we? 3 units. Okay? We need to really understand what's going on. So, translate by minus 3, 0, aren't we? Because we're translating it to the left. So, first of all, think about the graph y equals 2 to the power of x, okay? Now, when in doubt, work it out. You don't know what that graph looks like? Fine. Write down some values of x, write down some values of y. So I'm going to do minus 1, minus 2. Nope, that's the wrong way round. Minus 2, minus 1, 0, 1, 2, 3. Okay, I'm just going to work it out. There is no harm in you doing this. Okay, 2 to the power of minus 2 is 1 over 4. 2 to the power of minus 1, 1 over 2. 2 to the power of 0, 1. 2 to the power of 1, 2. 2 to the power of 2, 4. 2 to the power of 3, 8. Okay? So when you're plotting your graph, you know it's going to look something like this. We're going to cross here at 0, 1. We're going to have an asymptote on the line y equals 0. Because for no matter for what value of x, it's never going to equal 0 or go below that line. Okay? So this is our graph. Now it wants us to move it to the left, 3 units. So if I think this point 3, well this coordinate, if I didn't work it out, I have luckily, it's 8. Okay? It's 8. I worked it out. If we need to move it to the 3, this is now going to be our y-intercept, isn't it? So now if I draw the graph of y equals 2 to the power of x plus 3, it's going to look like this, where this is now 0, 8. We still have an asymptote on the line y equals 0 because we haven't translated it up or down, haven't we? Okay? The only thing we've done is shift it to the left. So there we go. That is how I've drawn my graph, and that's how I have sketched it. Don't forget to put your y and x when you're sketching. Oh, sorry, that's the line y. What's going on here? Y equals 0. Okay? So I've written my asymptote, I've done a sketch, okay? The other way you could do it, again, y equals 2 to the x plus 3. You could, if you want to, draw a table where you have your x and y, minus 2, minus 1, 0, 1, 2, and then you think to yourself, minus 2 is your x, so minus 2 plus 3 is 1. Okay? So minus 2 to the power of, 2 to the power of 1 is just 2. Okay? And then you'll go along and you could input and then draw it. Okay then, so I want you to give it a go. Think about, go back to, okay, what is the function here? Okay? What is f of x in this case? What have we done to f of x? Okay, so our function is a half to the power of x. It's a number to the power of x. But what have we done? Is it, well, what's going on? Okay? So, similarly here, our function is f of x minus 3. Okay, so that means it is a translation, okay, and we're moving it this time to the right 3 times. So it's a translation by the vector 3, 0. Okay, so if we think about the graph of y equals a half to the power of x, okay? So, it's actually the opposite, okay, of what we've just done. If we put in x and y, so we have, I always go for the standard, minus 2, minus 1, 0, 1, 2. If I put in a half to the power of minus 2, I'm going to get 4. Half to the power of minus 1, 2. Half to the power of 0, 1. Half to the power of 1, a half to the power of 2, 1 over 4. So what it's actually going to look like, just what we did, but a reflection in the y, isn't it? So it's now, going to look like, okay, we're still going to have an asymptote on the line y equals 0. Okay, and here it's going to cross at 1, 0. Sorry, it's not. 0, 1. Okay, so now what have we done? We've shifted it to the right 3 times. So this point here, minus 3, is now going to be our y-intercept. Now, I didn't work out minus 3, but if I think about a half to the power of minus 3, I'm going to get 8. So now our new graph, okay, is going to cross. There we go. We're going to have our asymptote on the line y equals 0. Our new y-intercept is 0, 8. Okay? Right, so what I want you to do, depending on how comfortable you feel, give this a go. If you're feeling really confident, I want you to do question 6, and I'm talking exceptionally confident. If you need a bit of practice, can you do question 5? So this is kind of, you're confident, but I'm going to put a tongue out, because it's like, you're confident, but you're not super confident to do an exam question yet, but you're confident doing a few of this. If you're really not confident at all, can we do questions 1 and 2? Okay? And then if you've just thought to yourself, what on earth has Miss been talking about? Don't do any questions, I'm coming to you. So, as we know, any number to the power of x will cross the y-axis, will intercept the y-axis at 1. On your calculator, you'll see a button for the function e. If you click e, just click equals. You get 2.7 something, okay? E is a number, just like pi. If you have a symbol pi, if you put pi into the calculator, press SD, you can get 3.14. E is also another symbol we use for a number. We're going to get to what E is and why we use it shortly, but for now, when you see the symbol E, just know this is technically 2.7 to the power of, and in this case it'd be 3x. So, we know that any number to the power of x, the basic graph looks like, not any number greater than 1 to the power of x. Looks something like this, and it crosses here at 0, 1. Okay, obviously if we had a number less than 1, we know that when we have a fraction, it reflects in the y-axis slightly different. But we know for the number 2.7 is going to look roughly like this. Okay? So this is what the graph of y equals e to the x looks like, roughly. Okay? And now how we sketch these graphs is we look at the equation. So it says sketch the graph y equals e to the power of 3x. Okay, what have we done to the function? Is it inside or outside the bracket? Inside the bracket. This is actually the function of 3x. Okay, if you think our original function is e to the x, this is what fx equals. This is now f of 3x. It's inside the bracket. What are we going to do? We're going to divide all of our x coordinates by 3, because we do the opposite. Okay, if we divide all of our x coordinates by 3, when we now sketch this graph, oh, that was the wonkiest straight line I've ever drawn. Okay, it's not going to affect this value here, 0, 1. It's not going to affect that value, because if we divide 0 by 3, still going to get 0. So we know it's going to cross there. But let's say this value is 2. If we divide it by 3, what's going to happen? Okay? Is going to be 1 and a bit. So what we're going to find is our steepness on this side is going to flatten down. Okay? But if this was 1, this value, if this was 0.5 and we divide it by 3, well, Well, it's just going to get smaller, isn't it? Okay. So how are we going to do this? Our new graph is going to look slightly different. It's still going to cross at 1. We'll get a different colour. Can you see how it's just not quite as steep? Our intercept is still at 0, 1. We still have an asymptote on the line y equals 0. There we go. We've sketched it. Done. Okay? Next question. Sketch y equals 5e to the minus x. What have we done to our function? We've multiplied it by 5, and then we have a minus x. Okay. What happens, first of all, let's think about this function. What are we doing to all of our x coordinates if it's minus x? Yeah, so if you think about our x coordinates, we're going to multiply them all by minus 1. If we multiply them all by minus 1, this now becomes a reflection in the y-axis. Okay, so essentially we're going to flip it. Okay, so reflection y-axis. Okay, and then what have we done to all of our y coordinates? We've multiplied them by 5. Okay. So our new intercept, instead of it being 0, 1, is now going to be 0, 5. So if I think back to my original graph, okay, it looks something like this. I now need to reflect it in the y-axis and stretch it. So our new graph, wonky line again. So our new graph is going to look like, I use a different colour pen, this. Okay, our intercept is now at 0, 5. Okay, we still have an asymptote on the line y equals 0. Okay, and we can see completely different. So then, the last graph. Okay, let's think about what's happened step by step. What have I done to the function? Remember, the normal function is e to the power of x. What have I done to the function? Well, I've divided it by 3, and then I've added 2 to it. Okay? So what's happening here? This is inside the bracket. Who does it affect? X. And what are we going to do to all of our x coordinates? Multiply by 3. Because we do the opposite. Then, inside or outside the bracket? Outside, who does it affect? Y. What are we doing to all of our y coordinates? We're taking away 2, so we're actually translating the graph. Adding 2. We're translating the graph. We're moving it up. Okay, moving up. So, again, I always think it's really good practice to think, what does e to the x look like? Okay, we know it looks like this. This is 0, 1. That's what we know. We know there's an asymptote at y equals 0. Okay, perfect. So, this time, what are we doing to the graph? So, we're multiplying it by 3, all of our x coordinates. Does that really affect us? Not really, okay? We just changed the numbers on the axes. But we're adding 2. So if this graph is shifting up 2, my new intercept is going to be at 0, 3. Okay, so here we go, 0, 3. Now I had an asymptote on the line y equals 0. If I've added 2, where is my new asymptote? On the line y equals 2. There you go. Okay. Now, you'll see in a lot of the books, here I always write the asymptote y equals 0. I always write it. You'll see in the textbook they don't always write it. But what happens is when we then get to a question like this, where we're translating it up, people forget about the asymptote and lose marks. Okay? So this is why it's good to get into the habit and really understand that actually anything to the power of x, okay, especially a positive number that's bigger than 1. That's what I'm talking. When I say anything, I mean a positive number greater than 1 to the power of x is never going to give us a negative value. Okay? So it's never going to cross that line. So please do remember that. So test your understanding. Okay, and I'm going to put this one as minus. Yeah, let's do -1. Okay, off you go. You've got this. Okay, so if we think about what's happened to our function f of x. Okay, we know f of x is e to the power of x. So what have we done to our function? We've multiplied it by -2, and then we've taken away 1. What does the -2 do to our function? Okay, it means it's a reflection in y-axis, and we're going to divide all of our x coordinates by -2 or 2. And then the -1 on the end, what have we done? Translated it down. So again, think back to our original graph that's going to look like this. Crosses at 0, 1. We've now moved it down 1, so it's going to cross at the origin, 0, 0. Our asymptote has moved down 1 because our original asymptote was on the line y equals 0. And it's going to be a reflection in the y-axis. Okay, so now it's going to look like, nope. Oh, that was terrible. Wait there, everyone. No, sorry, everyone might. This is shockingly bad. Let me try from the other way. Okay. Yep, that's a bit better. Okay, it's going to cross at 0, 0. And we're now going to have an asymptote on the line y equals -1. I'm just going to pass through the origin. Perfect. So what I want you to do now is, if you're super happy, question 5. I wonder if you're medium happy. Question 4, if you need more practice drawing graphs. Question 3. Right, so what we're going to look at now is we're going to look at the function, and the function, for example, y to the power of x, and we have the gradient of y to the power of x. Okay, there's a little animation which I'm going to show you on the PowerPoint because this isn't a PowerPoint, okay? So we know the number e is roughly 2.7, which is going to be in here somewhere, don't we? Okay? Now, the gradient of 2.5 is 0.92. You can see it's nearly, the gradient function is nearly the same, it's nearly multiplied by 1. And the gradient of 3 to the power of x is 1.1, which is again very close to 1. Okay, and the gradient function is very similar to the actual graph itself. Okay, so what we know e is 2.7, blah, blah, blah. It's actually called Euler's number, okay, or E-U-L-E-R, Euler's number. Okay, so for example, as we said before, you know, we have pi. It's something that's well known. Okay, and it's actually quite special because it has the property that when y equals e to the power of x, when we differentiate it, it is also e to the power of x. Okay? Even though any number to the power of x is known as an exponential function, e to the power of x is known as the exponential function. Okay? So, it's really, really amazing. Okay? And what we're going to do is we're now going to be differentiating e to the power of x. So here we go. When we are differentiating e to the power of x, okay, and this is going to come in handy. So when we differentiate e to the power of x, this is like differentiating using what I like to call a chain rule. But for now, you haven't been introduced to that. You're going to be introduced to the chain rule in the next 2 chapters. But for now, you're going to see the trick. In the next chapter, I'm going to introduce you to the chain rule, and I'm going to show you, and I'm going to ask you to show me how this trick works in comparison to that. Okay? So, the trick is, whatever you do, e to the power of x, okay, and this is e to the power of kx, what we do is, to differentiate it, we just multiply it by the differential of the x, which in this case, so e to the power of kx, what's the differential of kx? K, so we're just going to multiply that by k, okay? In other terms, if we had e to the 5x, when we differentiate that, e to the 5x stays the same, and then we multiply it by the differential of 5x, which is 5. Okay, differentiate e to the power of minus x with respect to x. So, to differentiate it, e to the power of minus x stays the same, and we multiply it by the differential of minus x, which is minus 1. So this becomes minus e to the minus x. Okay, and when we differentiate 4e to the 3x, 4e to the 3x stays the same, and then we multiply that by the differential of the power. Differential of 3x is 3, which gives us 12e to the 3x. Okay, now again, whatever your differentiation stays the same, and then you just bring it down, multiply it out, okay? Normally I'd do this step in my head, okay? And then just write this as the final answer, but I want you to really see what's going on. Again, when we look at the chain rule in the next chapter, you're going to see a bit more as to why this works. Okay, your turn. You've got 4 to do and 30 seconds. Okay then. dy by dx equals so we're now going to get 4e to the power of 4x. Okay, so we're going to bring that down. We're going to have minus a half e to the minus a half x. And then the last question, absolutely, 6e to the power of 2x. So, how confident are you feeling? Okay, now you know how to differentiate. We can apply all our knowledge from pure 1 and pure 2. So now we're going to have a mix of questions. You can see question 8, okay, we're given a function. It says, show that the tangent to the curve at the point 5e goes through the origin. Well, to find the equation of the tangent, you differentiate to find the gradient. Once the gradient and you have 2 points, you're able to do that. To start with, if you need to just differentiate, okay, I want everyone to at least do E and F. Then question 7. Then question 8. Okay, so question 8, here we go. The function f is defined as f of x equals e to the power of 0.2x. So f of x equals e to the power of 0.2x. I know if I differentiate that, I'm going to get 0.2e to the power of 0.2x. Okay? Then it says, show that the tangent to the curve at the point 5e goes through the origin. If it's tangent to the curve at that point, the gradient is that. Okay? If it was perpendicular to the curve at that point, obviously we'd do the negative reciprocal. But this is tangent. Remember pure 2? Okay, so the gradient for the tangent is in fact this at the point 5e. Okay, so 5 is my x coordinate, e is my y coordinate. So the gradient of the tangent. Now, m stands for gradient, the little t stands for tangent. I like to use this notation, you'll see it a lot as we get into tangents, perpendicular lines. Equals 0.2x to the power of 0.2 multiplied by 5, because that is the point at that point where x equals 5. E at 0.2 times 5 is in fact 1. So e to the power of 1, okay, what is e to the power of 1? It's just e. So that means that the gradient at that point is just 0.2e, okay? Fine. Now we know our favourite equation, y equals mx plus c. We have our gradient, we have our x coordinate, we have our y coordinate. Now we've just got to figure out c. It's nice and easy. Instead of writing y, I'm going to write e. Instead of writing m, I'm going to write 0.2e. Now you see, when I substitute, I use brackets. This, honestly, whenever I substitute, I use brackets. It just helps with mistakes. The biggest mistakes in A-levels are not adding your constant of integration, plus c, and is signs, really, is errors with signs. So I always like to just put brackets so I know what's going on. E is 5, and then plus c. Okay? Now, when I solve this, I get e equals 0.2e times 5. What do you know? It equals e. 0.2 times 5 is 1. So then it's 1 times e, which is just e, plus c. If I take away e from both sides, 0 equals c. Perfect. I now have my c, I now have my m. Therefore, okay, y equals 0.2e plus 0. 0.2ex, mx, plus c. But it's plus 0, okay? I'll just write that there for effect. Plus 0, but just so you can see, okay? We know that y equals mx plus c. Y equals m, our gradient is 0.2e multiplied by x plus c. But I'm deleting the plus 0, okay? So then, great, we've figured out the equation of a straight line. That's not what the question's asking for, though. The question says, show that the tangent to the curve at the point 5e goes through the origin. Okay, well, first things first. We want to show that it goes through 0, 0. Well, our y-intercept is 0, okay? So we already know it goes through something 0, okay? And does this equation balance out? When x equals 0 and y equals 0, I get 0 equals 0.2e multiplied by 0. So therefore 0 equals 0. Therefore, crosses through the origin. Okay? So, we're now going to be looking at the natural log, okay? And the natural log we like to call ln. Okay, so when I say ln, okay? Everyone repeat after me. Ln. Ln. Okay, this is ln. Now, ln is log to the base e. Okay? A ln is a log to the base e. So, Normally when we have log to the base 10, we just write that as log. That's it. Okay? A ln is a log to the base e, and we write that as ln. Okay? Now you're going to see why these are going to come hand in hand. And if we have a look, y equals x. Okay? And we have e to the x, we have ln to the x. Now what do we know about graphs that reflect in the line y equals x? They are in fact the inverse. Yeah. Yeah? Perfect. So, the inverse of y equals e to the x is ln to the x. The inverse of y equals e to the x is y equals ln to the x. Okay? So, a ln e to the x is in fact just x. And why does this work? This works because instead of writing ln x can be written as log to the base e of x. Okay? Now, when we think about this x here, it's not this x. This x is just a number. Do you know what? I'm going to change it. Log y is log e to the base. Ln y is log e to the base. Log to the base e of y, yeah? So, if I had ln e to the x, that's the same as log to the base e of e to the power of x. Okay? Now, using log laws, do you remember the law? I'll write it down here. Do you remember? Log to the base log x to the power of a can be rewritten as a log x. Yeah? Right. Do you remember that log to the base a of a equals 1? Okay, remember these from Pure 2. These are laws we should know, live, breathe, love. Okay? So, if I rewrite log to the base e to the x, this can be rewritten as x log to the base e of e. Log to the base of a number of that number is always 1. So therefore, that just equals x. Okay? So that's the proof of it. You don't need to know the proof, but instead of me just throwing a rule at you, you know what's going on. Same theory, the other way round. E to the power of ln x is in fact x, okay? They're inverses of each other. They cancel each other out. Just like times them by 3, then dividing by 3. Gone. Poof. It's just the same as multiplying by 1. Yeah? That's why they cancel each other out. So, nice and easy. Solve e to the power of x. Okay? So what I like to do is I ln both sides. Okay? Sometimes I say log both sides. But it doesn't matter which way. If we're logging it to the base e, which really, mathematicians are lazy, so instead of saying log to the base e of both sides, we're going to say ln both sides. There you go. Look, just missed out like 5 words. Right then, so I'm going to ln both sides because I want to find x. Okay, and the inverse of e is ln. So I'm going to have ln e to the x equals ln of 5. And you can see whatever was on the left-hand side is in a bracket. Whatever is on the right-hand side is now in a bracket. A ln e to the x cancels. We're just left with 1 multiplied by x. Now, when I say x, if this number up here was 4x, this would be 4x. If this number up here was 2x plus 1, this would be 2x plus 1. So then, this is going to give us x equals ln 5. Beautiful. Solved. Now, if we needed a numerical value for that, in your calculator, we have a button called ln. And you can put ln of 5 into your calculator and press SD. Maybe it wants it 3 significant figures. Who knows what they want? But at least you know how to get there now. Part 2. Solve 2 ln x plus 1 equals 5. Now imagine you are solving the equation 4 multiplied by x plus 1 equals 5. What's the first thing you're going to do? You're going to subtract 1 so that your 4x is on its own. Before you then do the inverse of multiplying by 4, you divide by 4. Same principle. We're going to take away 1 first, so we just have on the left-hand side, ideally we just want a ln x on the left-hand side, or an e to the power of x, okay? Now, so I'm going to get 2 ln x equals 4, and that's because I've taken away 1 from both sides. What's my next step? I'm going to divide both sides by 2. Okay? So, the 2's are going to cancel. How many 2's into 4? 2. So I'm now going to have ln x equals 2. Now I just want x. Now normally it's ln both sides, but we've got lns. So what are we going to do to both sides? E. Because the inverse of ln is e, inverse of e is ln. If I e both sides, I'm going to get e to the power of ln x equals e to the power of 2. I love my brackets. Always use them. It's law. E to the power of ln x. X. E to the power of 2. E to the power of 2. That's it. Unless it asks for 3 significant figures, always leave in exact form. Okay. I mean, we're going to go for a bit more of a harder example here, but I know that you can all do it. We're going to do this together at the same time. Okay, this is my favourite type of stuff. E to the power of 2x plus 3 equals 7. Step 1. We're going to learn both sides. So learn bracket e to the power of 2 plus 3 equals learn bracket 7. This is so clear that I've learned both sides, it's ridiculous. Ln bracket e to the power of 2x. The ln and the e are going to cancel. It's going to leave me with 2x plus 3 equals ln of 7. Okay. Just solving equations now. What am I now going to do to both sides? Take away 3. Minus 3, minus 3. So I'm going to get 2x equals ln. Now, I got rid of the bracket then, but I'm going to put the bracket back in. Ln of 7 minus 3. Okay? This isn't ln of 7 minus 3. This is ln 7 minus 3. Okay? This is somewhere where people get sometimes confused as well when they're then putting stuff in their calculator. And then I'm going to divide both sides by 2. So x equals ln of 7 minus 3. All of that is over 2. Okay? I can change this up a bit, and we should be really happy by writing this. Over 2 means half. Okay? I'm going to split it up. So I'm going to have half ln 7 minus 3 divided by a half. No, it's not. It's 3 multiplied by half. 3 over 2. Okay? I prefer to leave it like this. And what you find is, this isn't, this is obviously going to be part of the question. Okay? This isn't going to be the whole question, right? This is going to be part of a question, and you're probably going to have to do something after it. Leave it in this form. It's so much easier than to have this whole thing divided by 2. And we should be fairly confident at doing this, okay? Right, quadratics in e to the power of x. Okay, so this is something that people always get confused in. Whenever we talk about x, if I talk about x, I'm just talking about unknown quantity. Okay, think about this normally, okay? So we have e to the power of x is essentially just an x, isn't it? It's an unknown quantity, because here, e to the power of 2x, using laws of indices, we could write that as e to the power of x squared, plus 2 lots of e to the power of x, minus 15 equals 0. Now this should look very similar to something squared plus something minus a number equals 0. What do we think? Quadratic equation. This is how we should see it, okay? So you can either substitute, say let e to the power of x equal y. There's no point really, just get comfortable. Two numbers that multiply to give you minus 15 but add to give you 2, 5 and negative 3. So we're going to have e to the x minus plus 5 and e to the x minus 3 equals 0. Okay? What can we do now? Well, yeah, so now we can double check. E to the x times e to the x is e to the x squared. 5 times minus 3, negative 15. 5 times e to the x is 5ex. Ex times negative 3 is negative 3ex. 5ex minus 3ex, 2ex. Okay? Then we solve it. When does this equal 0? This is when e to the x equals negative 5, and when e to the x equals 3. Okay. Exponential functions are always positive. Reject. E to the x equals negative 5. Then, how do I solve e to the x equals 3? Ln both sides. Ln of e to the x equals ln of 3. So that means x equals ln 3. Beautiful. Okay? It's absolutely beautiful. Okay, part 2. Similar problem here. This time we have a hidden quadratic. Why do we have a hidden quadratic? E to the x minus 2 over e to the x equals 1. Okay? To get rid of the fraction, I'm going to multiply everything through by e to the x. Because an exponential is always positive, we can multiply this function by this positive. It's not going to change anything. Okay? So if I multiply everything by e to the x, I'm going to get e to the x squared minus 2e to the x over e to the x. Now they're going to cancel. Again, I probably wouldn't write this much detail, but it's to make sure you know what's going on. Equals 1 times e to the x, which is e to the x. Can you see I've multiplied e to the x by every single term? Not just by one term on the left-hand side of the equal sign and one term on the right-hand side, by every single term. So this is going to leave me with e to the x all squared minus 2 lots, minus just 2, isn't it? And then I'm going to bring the e to the x to the other side, minus e to the x equals 0. I'm going to rearrange this so it's in our nice quadratic form. E to the x squared minus e to the x minus 2 equals 0. Two numbers that multiply to give me minus 2 and add to give me minus 1. Negative 2 plus 1, isn't it? Sorry. Negative 2 plus 1 equals 0. So that means that e to the x equals 2 or e to the x equals negative 1. Okay, reject our e to the x equals negative 1. As we know from the graph, our exponential function is not negative. Okay, and then e to the x equals 2. How to get rid of the e? We learn both sides. Now you can see when I learn both sides, I write it down. You should also be writing this down. Perfect. And that is our answer. Nice and simple. Okay. So, time for you to test your understanding. Okay, you've got 1, 2, 3 questions. I want you working in pairs, and I'm going to tell you your pairs. Okay, so I'm going to go through this very quickly. Step 1, how do we get rid of a log? And we're going to e both sides. So I'm going to have e to the ln of 3x plus 1 equals e to the 2. We know that e and the ln are going to cancel, so I'm going to get 3x plus 1 equals e to the power of 2. So then I'm just going to quickly rearrange this in my head. E to the power of 2, take away 1 over 3 is the final answer. Okay? For part B, again, we have a hidden quadratic. E to the x squared plus 5 e to the x minus 6 equals 0. Two numbers that multiply to give me minus 6 but add to give me 5, 6 and 1. So e to the x plus 6, e to the x minus 1 equals 0. I'm going to get e to the x equals minus 6, reject, please make sure you write that. And e to the x equals 1, so that means if I ln both sides, x equals ln of 1, okay? Now ln of 1 is in fact 0, isn't it? Yeah? So x equals 0, okay? Please don't get caught up by that. Then for the second one, I've got 2 to the power of x multiplied by e to the power of x plus 1 equals 3. So first thing I'm going to do is I'm going to ln both sides. So I'm going to get ln of 2x times by x e to the power of x plus 1 equals ln of 3. Now remember, a ln is still a log. It's just a log to the base e. So using log laws, we know the log of ab is the log of a plus the log of b, because they're multiplied, aren't we? So we're going to get the ln of 2x plus the ln of e to the x plus 1 equals the ln of 3. Okay? Now, again, log a to the power of b is b log a. Okay? So for the first one, we're going to get x ln 2. Okay? Then we know for the next one we have ln e. You know they're going to cancel, so we're just going to be left with x plus 1. And I'm just going to put that in brackets so we know that's attached to that. X plus 1 equals ln of 3. Okay? I now end up with okay, I've now got 2 x's. I've got an x ln 2 and an x on its own. So what I'm going to do is take away 1 from both sides, then factorise out the x, okay? Just like we would if we were rearranging, because that's what we want, isn't it? We want x equals. So then I'm going to have x ln 2 plus x equals ln of 3 minus 1. If I factor out the x, I'm going to get x bracket ln 2 plus 1 equals ln 3 minus 1, and then divide both sides by ln 2 plus 1. X equals ln 3 minus 1 over ln 2 plus 1. Okay, and there is the final answer. Okay, so questions for homework is I would like you to do the whole of question 5 and question 4. If you need more practice, please do question 3. And then as a kind of exam style questions, have a look at questions 6 and 8. Okay, so moving towards the last part of the chapter. So that was solving. Okay, now we're having a look at turning non-linear graphs into linear ones. And as I said, what we're going to do is we're going to rearrange it so that we can compare this against y equals mx plus c. And do you remember at the beginning of the chapter I said we could do that? And then we can do the same. Okay, there's 2 cases, polynomial to linear and exponential to linear. Okay, we're going to look at both cases and how we can do this. So here is an example of a polynomial to a linear. Okay, we're going to go through it step by step. So the table below gives the rank by size of and population of the UK's largest cities and districts. London is number 1, but it has been excluded because it's an outlier. Yeah, if you think about the population, it's really huge, isn't it? So we just excluded it. So what we have here is we've got the city, we've got the rank, and we've got the population. Okay? The relationship between the rank and population can be modelled by the formula P equals AR to the power of n, where A and n are constants. So, draw a table given the values of log R and log P to 2 decimal places. Well, it's actually fairly simple, this part, because I think that something happened, but this is supposed to be 2, 3, 4, 5, 6, okay? That's how sorry, there's a mess up configuration. Okay, so we just want to find out what log of r is. So log r, and we want to find out what log p is to 2 decimal places. Okay, well the first one is easy. We just do log 2 because our first r is 2. So we want to do log of r, first is 2. So what is log of 2? 0 point something? Okay. Okay, so 0.3. Okay, then we're going to do, the next one is log of 3. Okay, 0.48. It says 2 decimal places though, so that must be 0.30. Then we're going to do the log of 4. 0.6, but 2 decimal places is 0.60. Then we'll do the log of 5, because that's our next r. 0.7, but we're going to put 0.70 for 2 decimal places. Then it's the log of 6, okay, 0.778. So that's just 0.78 to 2 decimal places, okay? Then we do the log of p. So for the first one, p is 1 million, okay? So log of 1 million is 6. Then we do the log of 730,000. We're going to get 5.86 to 2 decimal places. Then we get the log of 620,000, 5.79. Then we're going to do the log of 530,000, 5.72. Then we're going to do the log of 480,000, 5.68. Okay? Perfect. Nice and easy. Then it says plot a graph of log r against log p. Okay? Now if it says log r against log p, that means log r is our new x-axis and log p is our y-axis. Okay? So we're going to draw a lovely straight line using a ruler. And remember, if my line isn't straight, it's because you need to go to Specsavers. Okay? Like if you think about our x and y, okay? You need to make sure, though, that I know I've written x and y, but you need to think, right, what is your x here? Your x is your log r, because it's log r against log p. And then your p, okay, is, so instead of writing y, you're going to write log p. And then what you're going to do is you're going to plot this, okay? Now, you are going to be given graph paper in the exam for this part if you're asked to plot it, okay? It won't be a sketch. But if you think 0.3, so if I did the scale as 0 and here is 1, it's 0.5, 0.25, 0.75. I know I'm doing a rough sketch. And then we have 6 and 5.68. To be honest, I'll probably do this with 6 and here is 5. So this is 5.5, okay? So here we go. So 6 and 0.3, roughly here. Okay, 0.48 and 5.86, roughly here. Okay, and then you keep going. 0.6 is here, 5.79, 0.77, and 0.78. Something like this, okay, roughly. I mean, it's just a guess, right? But you can see the points are correct. Then what you're going to do is draw a line of best fit. Okay, well, it's quite easy, really, because they're kind of in a straight line. Now, I am going to use a ruler, and I'm going to show you exactly. Oh, if we were to find the gradient of this graph, we kind of picked 2 points that were on our line of best fit. So these 2 points were on our line of best fit, weren't they? Okay, this point was 0.78 and 5.68. And then this point was our third one, wasn't it? So 0.60 and 5.79. Okay, just roughly. Right, so we know, what do we know about gradients of a straight line? How do we find a gradient? Yeah, difference in y over difference in x, okay? Now, a lot of people, sometimes they, you can use different points, but, I mean, we might not get the same answer as what the answer is in the textbook, but it doesn't matter because we've picked these 2 points because they were on my line, just so happened. So, okay, our gradient is m equals y1 minus y2 minus y1 over x2 minus x1, okay? So I'm going to get 5.68 minus 5.79 over 0.78 minus 0.60. So that is going to give me a gradient of is minus 0.6. Amazing. Okay, then my y-intercept. Okay? Well, if I look at the graph, and again, you're going to have graph paper. Where does this cross the y-axis? It's 6 point something, isn't it? Yeah? What do we think? About 6.2? Yeah? Remember, you're going to have exact, okay? I mean, we're guesstimating, but you're going to be able to see this exact. So 6.2, let's say. And how did we get that? Look at graph. Yep. Okay, so we found it, 6.2. Okay. Now, it wants it in, so it wants AN. Okay, now let's really think about this. Now, you won't have to work this out for everyone because you'll get to know this, right? P equals AR to the power of N. Okay? In our case, if we log everything, I'm going to get log of P equals log of AR to the power of N. Using log laws, A multiplied by R to the power of N, I'm going to get log of A plus log of R to the power of N, aren't I? Okay, that's what log P equals. So then log P equals log A plus N log R. Okay, everyone happy with those? Okay, now think about the equation of a straight line. I'm going to rewrite this in that form and in a different colour. Right, so y equals mx plus c. Okay? If I rewrite this equation, I'm going to get log p equals mx, so that must be the n log r, plus log a. Okay? So, in this case, think about equating coefficients, when we're looking at them. C equals log A. We've just worked C out. Does anybody know what C is? 6, yeah, we've done 6.2. So then, that means 6.2 equals log of A. Now this is log to the base 10. Do you remember how to solve log to the base 10 problems? So this means that A equals, anybody know? 10 to the power of 6.2. Do you remember this from Pure 2? Okay. Right, we're just going to pause for a second. Right, so if we had, so log is always to the base 10 if we don't write the base, okay? Log of x equals y, okay? This is in theory saying that 10 to the power of y is going to equal x. Okay? That's what that's saying. So that's what we're doing here. We'll go over a few more of that. So now we have a equals 10 to the power of 6.2, and it wants it to two significant figures, so we are going to have to work that out. Okay? And then it wants n. Now in our case, again, if we look at what's going on, our x is our log r. Yeah? So that means our gradient is in fact n. We already worked out our gradient. Okay? N equals minus 0.6. Was that exact? Did that come out exact, our gradient, minus 0.6? Oh, right, we need to always write down what it was. Minus 0.6.1 recurring, because what does it say in the question? Two significant figures, so minus 0.61. Okay, please never round early. And if it's a fraction, keep it as a fraction until the very end where you have to round. Okay? So, then what is 10 to the power of 6.2? 1584,893 point something. Okay, two significant figures, that's 16. 1, 2, 3, 4, 5. There we go. So there's our final answer. So exponential to linear, slightly different, but same. Okay, same but different. Yeah? So the graph represents the growth of the population of bacteria P over T hours. The graph has a gradient of 0.6 and meets the vertical axis at 0, 2. Okay, and I'm probably going to put here m equals 0.6. A scientist suggests that this growth can be modelled by the equation P equals AB to the power of T, where A and B are constants to be found. Write down an equation for the line. Okay? So, we know y equals mx plus c. Yeah? Our y is in fact called, what's it called? Log P. Okay, equals our gradient, they told us, 0.6. What did they tell us our x was? T. And our c is the y-intercept, which in this case is plus 2. I mean, that's beautiful. Okay? Now, using your answers to part A or otherwise, find the values of A and B, giving them to three significant figures where necessary. Okay. So, we're going to do the same, but different. Okay? How are we going to do it? Well, we know that P equals AB to the power of T. Log both sides. Log of P equals log of AB to the power of T. Again, we can rearrange this. A multiplied by B is log of A plus log of B. So log of P equals, are you happy if I go straight to this step? Log A plus T log B. Can you see? Because it was B to the power of T, but obviously using log rules, we need to be a bit more confident with skipping these steps. Okay, now we compare. We got log P equals 0.6T plus 2. Then that means that, and we're comparing it with the other one. Oh, it's not log, is it? Log P equals T log B plus log A. Okay, so I've put them in similar order. We can see straight away that 2 equals log A. Yeah? And what are we finding? B. And 0.6 then must equal log B. Because if we compare the two. So, log B equals 0.6. How do I find B? Remember, log is to the base 10. So that means B equals 10 to the power of 0.6. It wants it to three significant figures, so we are going to have to work this out. Then it says log A equals 2. So A equals 10 to the power of 2. I mean, lucky for us, that's 100. Okay, but I don't know what 10 to the power of 0.6 is in my head. So, 10 to the power of 0.6 is 3.9810 blah blah blah. It wants three significant figures, so b equals 3.98. Absolutely outstanding. Okay, then it says interpret the meaning of the constant a in this model. Well, if we started at a, okay, and if we think about the graph, it represents the growth of population of bacteria. Well, if we start at 2, that must be the initial size of the bacteria. Yeah? So, initial size of the bacteria. Full stop. Okay. Let's see what the mark scheme says. Yeah, maybe because it says interpret the meaning of the constant a. Maybe we have to write a is. Okay, maybe what I've written is not enough. Let's double check when we look at the mark schemes. As you know, it's a fairly new syllabus. Perfect. A gives the initial size of the bacteria population. Ooh. Okay, we might need to expand on our R's. As long as we understand the context, we can refine the wording, okay? So then, test your understanding. So, we are looking at exponential modeling, okay? So there are two key features of exponential functions which make them suitable for population growth. Fun fact, when I did my maths degree, we had a module on modelling, and I looked at the modelling of exponential growth of the rabbit population in Australia. So, with population growth, we typically have a fixed percentage. So it's like a fixed percentage a year. So if it's 10% a year, exponential growth, the multiplier is 1.1. If you remember back in GCSE when, you have compound interest, okay, and you're multiplying, the previous year, if it's an increase of 10%, it's like by 1.1, okay? And then T is the number of years. This is really similar to percentage. And the rate of increase is proportional to the size of the population at a given model, okay? So the 10% increase of a population will be twice as large as if the population itself is twice as large. So, the initial population is when t equals 0. Everyone should know that the initial population is in fact going to be on our y-intercept, okay? This is always our initial population size. And then when p equals 100e to the power of 0, because in this case, 100e is our model, to the power of 0, because it's our initial value, so our time is at 0, it's going to give us 100. Now, to find the rates of change, we need to differentiate. So if our model is 100e to the 3t, if we differentiate, remember, when we differentiate exponentials, e to the power of 3t stays the same. We differentiate what's up there. 3t differentiated is 3. We multiply that by our constant. Okay, so we're going to get 300e to the power of 3t. And then the initial rate of growth is when t equals 0. We substitute that in here. We're going to get 300 times e to the power of 3 times t, which is to the power of 0, which is 1. Okay? So, it's really simple. We just need to make sure we understand what's going on. Right then, here is an example for us to look at. Now, so the density of a pesticide is given pesticide in a given section of a field, P, milligrams per meter squared, can be modelled by the equation P equals 168 e to the power of minus 0.006 t, where t is the time in days since the pesticide was first applied. Okay. Use this model to estimate the density of pesticide after 15 days. Well, it's told us very clearly that the density of pesticide is given in a field, okay? Can be modelled by this. So, very simple. If it wants it after 15 days, that means our time is now 15. So, our density, P, equals 160 e to the power of minus 0.006, and our time has changed to 15. Okay, when I put this into my calculator, so this is when t equals 15, I'm going to get 146.2, and remember our units is milligrams per meter squared. Please make sure you do write your units. Part B says, interpret the meaning of the value 160 in this model. Now our constant here, okay, the constant 160, it's our coefficient of E. If you imagine, for when we put t equals 0, e to the power of minus 0.006 of 0, we're going to get e to the power of 0, which we know is 1, okay? So that means that our coefficient of e is always going to be our initial population size. Okay, when my time is 0, we actually have 160. So therefore, 160, okay, we need to read the question, is the density of pesticide, is the initial density of pesticide. 160 is the initial density of pesticide. Okay? Then, part C, show that the rate of change of the density over time, okay, dp dt equals kp, where k is a constant, and state the value of k. Well, first of all, we know to find the rate of change, we need to differentiate p. If I'm differentiating this one here, what I'm actually going to do is my e is going to stay the same to the power of minus 0.006t, but I'm going to multiply 160 by minus 0.006t. Okay, so if I write that down, so it's going to be 160 e minus 0.006t, and then I'm going to multiply that by the differential, which is minus 0.006. So that means my dp by dt equals minus 0.96 e to the power of minus 0.006t. Okay, so therefore, my k, in this case, equals minus 0.96. No, it doesn't. No, it doesn't. Sorry, I've read that question wrong. It wants it, sorry, kp. Okay, our p is actually this whole thing here. So what do I need to multiply this by? The minus 0.96. How do I get to here? What do I need to multiply by? Well, it's actually, I know this is our final answer, but the k, because our p is this value, it wants to know this bit here, so I've already written it down. Minus 0.006, okay? Because if you think our p is this whole thing, and it wants pk, so this is p, and what did we multiply it by? And that was that, even though I've written the minus 0.96. So, perfect. Part D, I'm going to do up here. Interpret the significance of the sign of your answer in part C. Okay, the sign is negative. So that means the population is decreasing. Okay, now we need to put this in context of the question. Remember, because if you think about it, if it was a positive sign, we'd have a positive gradient. This is a negative gradient, so it's going to be going like this. Okay, I know it's a curve, but it's a negative gradient. So that means it's decreasing. Okay, so if you just put like negative equals decreasing. Okay, now let's think about it in the context of the question. Okay, so it's talking about density of pesticide. So the density of pesticide is decreasing over time, yeah? So the density of pesticide is decreasing over time. Perfect. And then part E says sketch it, P against T. So for part E, you're going to draw your axes. Make sure you label it time and P. Now we know our initial starting value is 160. So I'm going to make sure I write that on there. Okay? And then what we know is that it's going to gradually go towards 0 because it's decreasing. And it is a bit of a curve. So it's going to look like that. Okay? So it's gradually decreasing towards 0, right? And your favourite phase, if in doubt, work it out, okay? If you're not sure, just, you've got P, T, just put in a few values of T, 0, you know, and then you could even do 5, 10, 15, yeah, just to see what it looks like over time, okay? So when in doubt, work it out. Okay, I would like you to try and do your own now because it's very simple. Really think about the context of the question, okay, and really think about what's going on here. Okay, so A. Okay, state its value when it's new. So that wants to know our initial value. So when it's new, our initial value means when t equals 0. So this is normally the coefficient, okay? Especially if it's a number multiplied by e to the power of t. If it was t plus 1, it'd be slightly different, okay? But when our e is going to change e to the power of 0, it's normally, so our value when it's new, and it's a car, is going to be 20,000. Now, we need to put units. It says euros. It clearly states euros in the question. So you need to make sure you're writing euros. If you do not, you will lose marks. Okay? Part B. Find its value to the nearest euro after 4 years. Okay, well, what's happened here? Our time is now 4. So I always write down what's going on. So t equals 4. So we're going to have v equals 20,000 e to the power of minus 4 over 12. Now you can see whenever I substitute my value of t, I always use brackets. Okay? And then 14,331. Now, it says to the nearest euro, so make sure that you write your units. I always write it out again. Perfect. Then part C says sketch the graph. Okay. So in my sketch, I've got my time, I've got my value. My initial starting is in 20,000. Okay. And my value is in euros. Please make sure you have your units. And again, we know eventually this is decreasing, isn't it? This is actually depreciation. So it's going to look like that. It'll eventually get to 0, but I'm not sure how long. Okay? Something like that. Maybe a bit more of a curve to it. Mine looks a bit wonky. Right? Nice and easy. Okay, so your task now, should you wish to accept, is question 2 and question 3 and question 4. So confident, 2, 3, 4. 6. And if you really think you get it, just go straight to question 5 and question 6, depending how confident you are, okay? So if you're really confident, 5.